This is the Advanced Extension Award from 2022. It's 3 hours long, you have no calculator, so you just got to sit here and think about maths really hard for a long time until you get stuff. This first question was by far the easiest on the paper. You just need to take logs of both sides, exactly like it says, where you set y equals first. And then of course you can implicitly differentiate this for 1 over y dy by dx, and you can differentiate that by just bringing the x squared down to the front, following log laws, and then doing product rule. And so 2x squared, so x squared is differentiated, so that's leave this alone, differentiate that. Times both sides by y, replace the y with the thing that's given, and then we're just going to set that to be 0 to find stationary points. And that will go rather well, because when we set that to make 0, this can't be 0 because it's an exponential, so that's not the case. This equals 0, therefore. Says x is greater than 0, so we can just divide by x here nice and safely, and then move the 1 over, divide by 2, and we end up with our answer to this question. So a very nice warm-up for us to get there. Next is a vectors question. The first half much easier than the second, I thought. Find it. So we've got FP. We've got like 5 different forces going on here, going this way, this way, this way, this way, and that way. So let's just find all the vectors we can here. This one firstly is minus p plus q, which I'll write as that apparently. Now this one here is the key idea to get here. This is going to be, well, it's a regular hexagon, right? It says so. So you've got a bunch of equilateral triangles in here, right? Because 120 degrees is the interior angle here. So you've got a bunch of equilateral triangles when you halve that down, which means that this length is just 2 sides of those equilateral triangles, and this length is 1. So this is just double this. And that's, I think, the insight that you needed to have to make progress in this first part of the question. So we've got this, and now of course we can get this just by going minus q plus this, and then of course we can get this because it's the same as that, because vectors don't care where you put them, and this is the same as that because again vectors don't care where you put them, and therefore we can find O to S is just this plus this, which gives us that, and I think we now have everything we need. The force is this, plus 2 lots of this, plus 3 lots of this, plus 4 lots of that, plus 5 lots of that, and you do some simplifying and you eventually end up with this. The magnitude and the acceleration of the particle is that. Given the mass is that, find the magnitude of p. Now I thought this was a really hard thing. Now we're obviously using F equals ma, but we need the modulus of the force, or the absolute value of the force, because we've been given the magnitude of the acceleration, so we need the magnitude of the force, I guess. Which is difficult to get because p and q aren't orthogonal vectors, is that the word, when they 90 degrees? So we can't just immediately do Pythagoras, right? That's not going to work at all. And they're different lengths as well, so that they're just, yeah, this just, what we need to do is we need to try and eliminate q, obviously, to then get p. And this is a hard spot, but if you write our, I mean, firstly, 120 degrees in there, 30 degrees in there, I think I'm going to use that for something in a second. But yeah, like I said, I need the magnitude of r is 3 times 13, not just r. Obviously, otherwise it wouldn't make sense. But here we can write this as this, and now why would you want to do that? And how on earth would you spot to do that? Well, what's great about this is q minus p is one of the sides of the hexagon, and it's a regular hexagon, so q minus p has the same length as p. And so now I have r written in terms of 2 vectors that have the same length, which I didn't before. So that's quite good progress. It's not perfect because they still don't meet at 90 degrees, but I think I can fix that, because let's pretend that r is going in this direction somewhere. We've got like a lot of q minus p, like 21 lots of it, q minus p in this direction. And then we've got minus 6p, p of course goes here, so minus 6p goes in this direction. So this is kind of what r is made of, right? It's this and then this. This angle here, I mean, if you put the minus 6p this way, you've got 30 degrees and then another 30 degrees. It's just half of the 120 that's in this corner here. So that's the 60 degrees there. And now I think we can just do cosine rule to find r, or the modulus of r, because, again, this length is the same as that length. So we could just call, we could call the modulus of p just like p without, just without bold, just like a letter p. And that length, if we scale it, this length here is going to be the same as this length here. It's not. This is 21 times that same thing, and this is 6 times that thing. But it's the same. We can pretend now that's the same length, so we can just write some p's instead of all this, because the diagram shows that they are the same length. So we can do cosine on this, just replacing that and that with these p's here, and then it's just plain sailing, right? Cos 60 is a half. You end up getting this if you just spend a bit of time doing that. You square root, obviously. And now again, you could be more intelligent here and not get to the 351 and like factorize out some numbers so you get to this easier. Or of course you can just kind of do a prime factorization of this and see that it's 9 times 39, which therefore makes root 9 3, and then root 39 p squared obviously goes to p, and then we can put this into here and we can eventually solve for that p value. And this thing here I've just called p here because I couldn't be bothered to type this every time in PowerPoint. That's quite annoying. Question 3 then, so we've got use the formula for these, well they're in the formula book to prove this. Well, tan is just sine over cos regardless of the angle. We now use these things here, so it's sine cos sine, and then if there's a minus you use a minus, so that's that one. And then it's cos sine sine, if there's a minus you use a plus, so we've done that there. Of course sine 90 is just 1 and cos 90 is 0, so this goes away, and we just get this over this there, which is of course cot theta, which is the right hand side. Part B is much more interesting, obviously. There's a few ways you can do this. Again, it's one of those things that you have 3 hours, you just need to try stuff. Something might work eventually. I wrote this as this, obviously. I can write this as well. I then just decided to times everything by cos of this to get 2 cos of that there. This goes to just one of them there, and then this goes away. And then I thought, why don't I just do that again? So I did it again, and the reason that's really helpful is because, well, it gets rid of this fraction, which makes it feel like a natural thing to do. But actually it does much more than that, which is 2 cos squared of an angle minus 1. That by definition is just cos 2 of the angle, and 2 sine cos is sine 2 lots of the angle. So I think we end up with this, just following, the double angle identities you get when you think about these a little bit harder. And that's really cool, because now we can just divide both sides by sine to get cot of this double angle here. And now we can just compare this sorry, we can't just yet, can we? Apologies. Now we have to use what we got in the first part, which is tan of 90 minus theta is cot theta. So let's look at this here and try our hardest to write that as tan of 90 minus theta. Well, I think we can do it if we just do this. 90 minus 124 is minus 34, minus makes a plus. And so I think we can use this. This is equal to this, which means that's equal to cot of that bit there, based on this identity, just replacing theta with 124 minus theta. And yeah, put that in there, and now we can say this thing here has got to be equal to this thing here, which gives us one solution for theta. However, I'll put a comma here because of course there are going to be more, because what if this graph, say, was shifted 180 degrees to the left? Well, then you'd have this thing here equal to this thing here plus 180. And so you can solve that for theta, and then you can keep going, and you just need to find all of it. You keep going, you add another 180, you add another 180, and keep going until you get to a theta value past 360. And now you could start taking away 180, but that gets you negative theta values immediately, so we won't use those. These are all the other values you get, and that will be our full answer. Question number 4 then is, well, differentiate e to the f of x is just f dashed of x e to the f of x, so that's nice and easy for 2 marks. Curve C1 and C2 are these things, so of a similar form, I guess. Find the x-coordinates of intersection, so set this equal to this, I guess. Cancel these things out because those things aren't 0. We saw the idea that exponential was 1, 0 earlier. Now this is kind of interesting. X can't be 0, so we're safe to divide by x here. We can rearrange this. This is just a quadratic, essentially. We can factorize it straight away if you want to. Get solutions of plus minus root 2 of 3 or plus minus 2, except then root 2. Except they're not plus minus again because it tells us x is positive, so we just get these two bits here. Given that C1 and C1 lies above C2, between these 2 points of intersection, find the region bounded. So we're going to have to integrate this one between, is it C1? Yeah, this is C1, so this one's above. So let's integrate this one between here and here, take away this one between here and here. But actually, if you're integrating across the same bounds, you can actually just put that integral across into one integral, rather than 2 separate integrals. Now, of course, we can factorize the exponential to get this. And again, 3 hours, you've just got to stare at this and think, how on earth are you supposed to do this integral? And, I mean, you could consider lots of things. You want to try and think about this, right? Again, this is called a stem of a problem, and it's trying to help you out with the main task at the end here. Like, so how is this helpful? Like, how could we force this usefulness into here? Well, if you factorize out an x from here, or even just a minus x, you have this left over, and you might recognize that because that was written on the screen about a minute ago, and it factorizes. And in fact, more than that, it factorizes beautifully, by which one factor is the thing that we need in front of the exponential to end up with derivative. And so now it becomes very natural to think, well, we could just do an integration by parts now, because that one, essentially this whole thing we could take as one bit, and we could integrate it very easily because it just integrates straight to this. Of course, I can multiply this by minus x to end up here. And now I'm going to do exactly that. I'm going to integrate by parts. I'm going to integrate this one a couple of times, leave this one alone the first time, and then differentiate it the second time. So if you didn't understand what I just said there, that's not surprising because most people teach integrating by parts in the normal way, which I just think is really weird. Just integrate, you pick your 2 bits. This is 1 bit, this is the other bit. You integrate 1 bit twice, so here and here. You leave the other bit alone, and then you integrate it, then you differentiate it the other time, and smash in a minus integral in the middle. I should probably have some evaluated between stuff bits here, but I couldn't be bothered to type them, or I just forgot. I'm not really sure. It's not going to make a difference because I'm going to just evaluate it all at the end anyway. This integral now we have to do is actually really cool as well, because if we just put this minus into here, we end up with this, and that's already, it's perfect. So we just integrate that. Yeah, now we can just evaluate the entire thing between the 2 limits. When you do that, something quite interesting happens, because this, clearly 2 root 2, but root 2 cubed is just root 2 times root 2 times root 2, which is root 2 times root 2 is 2, times root 2 is 2 root 2. And so you get lots of cancelling up here. A similar sort of thing happens when you put in root 2 over 3. But it's not quite as effective. It still works quite nicely though. You end up with this. I'm not going to talk too much about the mechanics of this. You end up with just some answer here, which is an exact numbers in this form. Is this of this form? I'm trying to decide. Is that of that form? So it's a number. Yeah, that's there. That's fine, I think. Yeah, cool. Question number 5. So we have, it took me a while to draw this picture. What I drew was this. This is the aeroplane. This is the light aircraft. The light aircraft is in the air, going at 2v this way. The aeroplane is on the ground, but just taking off with a speed of v in this direction, theta here. It's d horizontally in front of the light aircraft, which is 3 kilometers up. So that's my picture. Tan theta is this. If you've done, which of course you have A-level mechanics, you know that if tan theta is 3/4, that means sine theta is 3/5, and cos theta is 4/5. That's just the 3, 4, 5 triangle doing some SOHCAHTOA, so that's cool. That means that this speed here is v cos theta, which is 4/5 v, and this speed here is v sine theta, which is 3/5 v. And now speed equals distance over time, clearly, which means distance equals speed times time. So if we want to draw this diagram like t minutes later, or really actually, sorry, t hours later, what happens is this plane, well, let's think about vertical first, because there's only one thing going on. This plane closes the 3 kilometer gap at a speed of 3v over 5, which means after time t, it will have moved up 3v over 5 times t distance. So this gap will have gone down to 3 minus 3v over 5t, and that would be our new vertical gap. And likewise with the horizontal, the new horizontal gap will be d minus, well, this one's closing the gap, isn't it? So d minus 2v times t, and then this one's widening the gap, so plus 4v over 5 times t. I've put minus here and plus here. Should I have done that? I'm wondering whether I'm correct about that. I'm absolutely not. I've written this wrong around. So this should be a plus, this should be a minus, and then you do end up with this, I think. If that's a plus and that's a minus, you do end up with that. I've just typed those up the wrong way around. And now, of course, if the distance between the planes is d, big D this case, instead of little d, of course, d squared is equal to this squared plus this squared. And you've noticed that I've got these the other way around, but that's okay, because when you square numbers, it doesn't matter whether you square positives or negatives, so I can just take out a factor of -1 for both these things, and we'll end up with this, and I can't be bothered to type that up. So anyway, we get to the next bit. Given the distance is never less than 2, so d is always bigger than or equal to 2, which means d squared, of course, is always bigger than or equal to 4, which means this whole thing here is always less than or equal to 4. Sorry, is always bigger than or equal to 4 as well, because it's equal to d. Sorry. Yeah, cool. Good. So, okay, this is complicated. What I did here was I expanded out this. Maybe that's not the smartest thing to do, but I'm not the smartest person ever, so we'll have to just deal with it. That's done. So next what I did was I grouped, obviously, the t squares and t's, and now what I said was, this has no solution. This is a quadratic in t, right? is a quadratic in t, and it's always greater than 0 or equal to 0, which means it either has no solutions or one solution, which means that its discriminant is always less than or equal to 0. Its discriminant is this thing squared minus 4 times this, and that's always less than or equal to 0. Okay, so then I did some more maths. I put these things together, I think, and I sort of put that together a little bit. I factored out a 6 here, because then I could square the 6 separately to make a 36, which I could then cancel because there's a 0 over here. So that's quite cool, I think, what I did there. All the v squareds cancel, which is marvelous. And yeah, the 36s can cancel. You can times everything by 25 if you want to. You can cancel this 36 as well. You get this, which ties up to this. And this is not too hard to solve. It doesn't factorize. You just have to complete the square or use quadratic formula or whatever. And you end up with d is this. And now we want to be greater than or equal to 0. So our solutions will be either side of the two critical values. So it will be d is less than the smaller one, which is this, or d is greater than the bigger one, except d has to be positive, right, because it's a distance that was initially set between the planes. So we'll just add a quick bigger than 0 there, and I think we'll end up with our entire answer. Good. Question number 6 is just the worst thing ever. I don't know whether I was meant to enjoy this question, but I certainly didn't. This is the whole thing. We're going to do it in parts. The one saving grace is that it's so broken down into parts that you could actually get quite a lot of marks on this question, even if you didn't really understand what the hell was going on, which is certainly what describes me whilst doing this question. Anyway, you have a length of 4 going across here, and then you break it up to make each section a quarter of the line before it. So after a length 1, you break it, and then you do a length 1, and then you break it and do a length 1, break it, length 1, and so on. So they're all just length 1. And then the next iteration, you break this length of 1 into quarters. So you have a quarter, a quarter, a quarter, a quarter, a quarter. This length you don't break up, because you only break up the horizontal ones. But it just repeats the same thing that was going on here, right? So it's just, this length is 1, and then you have a bunch of quarters. This length is 1, and then you have a bunch of quarters. And the first 2 marks is just asking us, essentially, this arrow is pointing at all 3 of these things. It just, yeah. Essentially, so yeah, 5 lots of a quarter is just 5 quarters. That's all of that. Then just 1, and then another 5 quarters. You get 2 marks for just adding up that all together, and you get the answer. Write down the number of line segments that are parallel to L0. So essentially, write down the number of line segments that are horizontal in Ln. Now, each horizontal line segment, every time you do this iteration, breaks up into 3 horizontal line segments. So this one has 1, which then goes to 3. And then each of these 3 break up into 3 bits themselves. So you have 9 here, and then each of those 9 break up into 3 further horizontal bits. So you have 9 times 3 is 27. So the line segments in Ln are just 3 to the power n, because it's 3 to the power 1, 3 to the power 2, 3 to the power 3, so it'll be 3 to the power n. Sloped line segments in L2 that are not in L1, so not counting these 2 bad boys that always stay where they are, well, you just have 1, 2, 3, 4, 5, 6. Thank you for giving me a mark for counting. New sloped line segments that are created by the nth plus 1. So, okay. Every time you break up a horizontal line segment, you create 2 slopey line segments, 2 new slopey line segments, I guess. So, for example, here we broke up 1 horizontal, we got 2 slopey ones. Here we broke up 3 horizontal line segments, which gave us 3 times 2 slopey ones. And here we have to break up 9 horizontal line segments, which are going to give us 9 times 2, or 18 horizontally ones. The formula is going to be 2 lots of 3 to the n. Created by the nth plus 1 means you're looking at the previous one. So that's why I've just used 3 to the n. So here, there are 6 of them because it's 2 times the previous 3 to the n. And the next one I said was 18, didn't I? 2 times 3 squared. So to get to 3, you use 3 to the 2. And to get to 2, you use 3 to the 1. So that's why there's just a 3 to the n there. Hence find the length of Ln as n goes to infinity. To do this, you need to think about the slopey bits and the horizontally bits separately. So let's do the slopey bits first. So in L0 there are no slopes. I've called the length of slopes S. So there are S0 is 0, there's no slopes in this. S1 is just 2. You can put 0 plus 2 to be fancy, just because of the thing that's going to happen next. S2 is, now be a bit careful here, it's 0 plus 2 obviously, plus all the new ones, which we've kind of already said is 3 times 2 to get how many new neurons there are, 6, times a quarter because they're all a quarter of the length of the ones before. Now S3 is going to be 0 plus 2 plus those ones, plus another 3 lots of 2, done 3 more times, and then a quarter squared, because you'll have quartered them down once again from where they were before. You've quartered these ones down, so that's why there's another square there. Now here we said there was 3 horizontals, each making 2 slopey ones. That's where 3 times 2 comes from. And the next one we decided there are 3 separate pairs of slopey things, each creating 3 sets of 3 horizontal ones, each creating 2 slopey ones. So that's 3 lots of 3 times 2 there. And we end up with a pattern, of course. I'm going to go with Sn plus 1, just because then I can write a 3 to the power 0 here maybe, and then a 3 to the power 1 here, and then what you notice is the last term, because of course you just keep adding extra ones in, the last term has 3 squared here and a quarter squared here, and that got you S3. So if you're using Sn plus 1, you can finish on n's, which is just quite nice. So we'll just finish on n's if we go to there. So okay, that's that done. And now we need to think about, and also of course we can write that as a series sum. You can factorize out the 2's because they're not doing anything, they're just 2's. And then you can put these 3's into this 3/4 because the powers match every time to make 3 over 4 to the r, and then you're going from r as 0 to n. You could have also put a 1 to the 1/4 to the power 0 here, I guess, as well, just to make that pattern even more clear. But anyway, we end up with this. The horizontals then, or the flats, I just called f0 and f1 and so on. Horizontal length here is 4. The next one is just going to be 3, isn't it? You can be fancy and say it's 3 lots of a quarter of the original 4, because remember you're quartering it and you're going to have 3 of them. The next one is going to be, again, 3 lots of 3, which is 3 squared, times a quarter squared, because you've quartered them twice now, times the original length of 4. And of course the pattern here is much easier to get, I think. Go to fn plus 1 again to match this n plus 1, but we'll go to 3 to the n plus 1, we can just see that the powers perfectly match the numbers here, with just this 4 hanging out at the end. Now that's a little bit annoying, but it's okay, because what we could do maybe is we could write it, why have I written that twice? Excellent. We could write it like this, right? Where we put this 4 into here to reduce that power down to just an n, because of course this 4 is on the top, not the bottom. And then I could break this down into a 3 times 3 to the n, and then I can put the 3 into there, and I end up with this. And so the length of the total line is the slopes plus the flats, which is this plus this. And we're just going to send n to infinity and see what happens. Now if we do that, clearly this is going to go to 0. It's not part of the sum, of course. This is just going to go to 0 because 3 to the n just goes to 0 as n goes to infinity. So we're actually just looking for the length of the line to just do this as n goes to infinity instead. It will approach whatever this approaches. This is a geometric sequence with what's it even called? The ratio is less than 1, or the modulus of the ratio is less than 1, so this is going to work, right? We can just use the a over 1 minus r formula. The first term is clearly 1, because this to the power 0 is 1, and then r is 3/4, so it's just going to be 1 over 1 minus 3/4, times the 2 that's outside. This makes a quarter. 1 divided by a quarter is 4, times 2 is 8, and we'll have that bit done. Good. Next bit, so the area enclosed this time, so we're talking about areas now, between L0 and Ln is AN. So like if you put L0 here, it's looking for the area enclosed between the 2 bits, which is obviously just a trapezium here, which is actually what we have to do for the first bit, is find A1, which is the area between this one and this one. So of course that distance is 2, because 1 plus 2 plus 1 is 4, which if we draw a line coming down here maybe, this angle here, I think, well actually no, I didn't need angles. This length is 1, so 1 plus 1 plus 1 is 3, so the 2 spare bits must be a half each, so that's a half there, to make 1 plus a half plus 2 plus a half plus 1. Sorry, to make 1 plus a half plus the 1 across here, plus this half plus 1 make 4. And then we can just do 1 squared minus a half squared to give us root 3 over 2 as the height of the trapezium. And then the area is just 1 plus 2 divided by 2 times the height, and we'll have our area for A1. Now what happens when you do an plus 1 minus an? So let's think about what happens when you do L2 minus L1. Like, this original trapezium that we just kind of worked out is going to cancel out, right? Because L1 fits underneath L2, and all that's going to be left is this little trapezium, and this little trapezium. So there, we're going to have just, okay, actually what I've done here, as I said, the entire area of this is the original trapezium we just worked out, plus 3 lots, that's where this 3 is, 3 lots of a quarter times that original area. Now it's a quarter times a quarter because the trapezium has been, the length scale factor from this trapezium to this one is a quarter, right? Because all the sides have been quartered down. But we're thinking about areas here. So that quarter is going to have to be squared because areas work with square scale factors, don't they? So I could have just written a quarter squared here, but I decided to write a quarter times a quarter. Now the next one is of course going to be the original trapezium plus what we just had, plus the 9 little trapeziums you come up with here. Of course 9 we can write as 3 squared, it's 3 lots of 3 extra bits coming up on each one. And then we've of course got our same scale factors we had before. This is the area of one of these trapeziums, and we're going to quarter that down by scale factor a quarter squared, because again it's an area scale factor, so it's going to be a 16th times a 16th. And we can keep doing this, of course. And now when we do like an plus 1 minus an, like this minus this, the front 2 terms cancel, and you're just left with the last term. So this is just going to be the last term, which is going to be, well, this is area 3, isn't it? And we can see there's powers 2 here. So we're going to have this minus this be, I've just written this like this just to be super clear, but we're going to have n's here. Because if we did A3 minus L2, this minus this, we'd end up with 2's in the powers. So we're going to end up with n's in the powers here. And we make this. Hence find the value as n goes into infinity of an, so not of this, but of an. So okay, well, we could tidy this up a little bit. I guess we could put the n's together like this, and that's the area of the difference. Now that means that the area of just an is essentially just all of these terms added up to n, because, you know, remember, all we were doing here is these are just 3 to the power 1s and 1/16 to the power 1, and then I guess there's 3 to the 0s and 1/16 to the 0 here in this term. And this bit here just meant you cancelled all the previous terms, but if you're just thinking about an, just like this is a3, you just have all of those terms from n is 0 all the way up to n is n, I guess, or whatever. So an is just going to be the sum of all of those terms, and I've tidied it up just to have one thing here. And we just have to deal with this. Of course, this is a constant, so it can come out to the front, or we can just consider it a, I guess. When n is 0, this just goes away and becomes a 1. The ratio is 3/16, so it's just going to be that same formula, a over 1 minus r, this divided by 1 minus this, and we end up doing some maths, and we eventually get to this as our area. So I've just put that over there, and we've just got one bit of this stupid question left. The same construction as described above is applied to 3 sides of a triangle length a. So we've got an equilateral triangle length a, and we're going to do this same kind of idea to all of the sides. So this side here is going to become crooked and fractal like this is, and so is this side, and so is this side. So, and it wants us to say, when it's done that, like limiting, so when you're doing that to all 3 sides loads of times, the resulting area is this. Now the area of the original triangle, of course, is a times a half times sine 60. Of course, this angle is 60. Sine 60 is root 3 over 2, so we get this. And now, when we do these fractal things on this side, we're just going to get, and we limit it to infinity, we're going to get this 3 times on each side, except this was the thing when the original length was 4, and now we have the original length a. So if we say from here to here we have a scale factor of a divided by 4, of course a to get it becoming a divided by 4, so divide by 4 to get this to a 1, and then times it by a to get to this. So the length scale factor from here to here is a over 4, but we're thinking about areas, so we're going to have to square that scale factor. So the limiting area of this triangle is going to be its original area plus 3 lots of this times by, just that bit, times by a squared over 16, this scale factor squared from here to a side of the triangle. and that's apparently equal to 6 root 3. And then you just solve this. I cancelled out the root 3's, obviously, that became 3/4. I did some stuff. Not too happy with how I did this, I guess. I mean, here you just halve both numbers. Thankfully, I do know my square numbers quite high, so I did recognise that as 26, but otherwise that may have been annoying to try and get. But anyway, a much better question to finish up then that was just in every way superior to what we just did. A circle AB has, or centre AB has radius r, so that's clearly this circle here. And show this, so 2 marks just for literally putting this into there and then doing some smart algebra. I've highlighted C and B because what I'm going to do, just looking at this here, is when I expand out this term, I'm going to pretend C minus B is just one thing. So it's this thing times itself is m squared x squared, and then plus 2 lots of mx just times this, and then plus this thing squared, and that keeps it in the form that they wanted it there. Then we just factorize the things to make it look like they've got it, and we get 2 very nice marks. Given L is tangency, that of course means b squared minus 4ac of this thing is 0. So okay, well b is this, a is this, c is all of this. So let's set that to equal 0. This is not that easy, but we can do a few things. 2 squared is 4. This thing squared, again, I kept the c minus b together, and you'll see why. Didn't do anything with this at all. Then I expanded this out, and something quite nice happens here. Minus 4a squared comes from this second term here, cancels with that. And also, I think it's this bit here. All of this cancels with the first bit from here, but not the second bit, of course. We still have a minus 4 there. So we end up with this. I think I divided all that by minus 4 to get this. And now, this is a quadratic. It's a quadratic in c minus b. I've made a couple of videos talking about this idea, but I can just bust out the quadratic formula here. And because there's a c minus b here, and a c minus b squared here, and nothing to do with c minus b here, I can just say c minus b equals the quadratic formula. Minus b here, where b is this bit here, because it's attached to the c minus b. This is confusing, of course, because these b's don't refer to these b's, but whatever. They love doing that. They love giving you quadratics in a, b, and c, and then making you confused over this. But anyway, so this is b squared. This is 4 times a, which is just 1, times c, which is all of this. And thankfully, lots of stuff cancels here, which is really good of it. The stuff cancels inside here. Root 4 is 2, root r squared is r, and divide all the 2's, and then add the b, and we end up with what they wanted us to get. The circle C1 has this equation, and C2 has this equation. Find any lines that are normal to both. Just draw a picture. This is the circle center 0, 0, radius 4. This is center circle, halve that for 10, halve that for 5, and then you get 100 and minus 25, and you actually get 36 on one side to get radius 6. I couldn't be bothered to write it down. That's this circle, obviously, and the other circle looks a bit like this, maybe. It doesn't really, because if this is 10, 5, then it's 5 above the x-axis, so it should reach down below the axis, but I couldn't be bothered to draw it particularly accurately. I later drew it accurately, which is what helped with something that's about to come up. But anyway, this is roughly the picture. Now, this distance you can very quickly work out is bigger than 10. I mean, you know it's bigger than 10 because this horizontal length is 10, so hypotenuse is longer. Now, the reason that's important is because it means the circles don't touch, and that means the only normals that it can exist to both circles is just this one here, which has gradient 5 over 10, which is a half, so it's just y equals a half x, and that's the only one that exists. Now it says find all lines that are tangent. So let's look at this picture again and think, okay, how many lines are there that exist that are tangent to both those circles? And I think you can come up with 4. They look a bit like this. Now, this is where you want to draw your picture a little bit more accurately, I think, because what you can notice if you do is that this distance across is 4, because that's the radius of this circle. This is 10 here, and the radius was 6. So actually, these two circles reach across. This circle reaches across the line x equals 4, this circle reaches across the line x equals 4, and this tangent should be a vertical tangent with equation x equals 4. So if you draw your picture actually decent, and you've got 3 hours, so you may as well draw it decent-ish, you got a free mark for that, for finding x is 4. Now you can find that algebraically, but it's nice to know that you can just find that anyway. Now otherwise, how do you do this? Well, of course, you did all these 8 marks of work to get this, So let's use it. Right? We're being asked about lines that are tangent. We know that if lines are tangent, this must be true. So let's just pretend our lines are of the form y equals mx plus c. And let's put that, now this one has a is 0, b is 0, and r is 4. So let's put that into there. And we get, and then let's also, this one here, remember, had a is 10, b is 5, r is 6. So let's put that into there as well. Tidy these up a little bit, you get these two. And of course, let's just set these two c's equal to each other, and we get this. Now there are four equations that come from this. There's the plus plus one, there's the plus minus one, there's the minus plus one, and there's the minus minus one. So we have four equations that we need to try and solve here, one by one. So let's just start with the top one. This actually turns out to be the worst one. So anyway, let's take away 6 lots of this thing here. Let's square both sides to get rid of this square root. When you square this, of course, it's this thing times itself, 5 times 5, 5 times minus 10m, so on. This obviously just squares to 4. You get this, you've got 3 hours, stare at it hard enough until you find the factorization, which is this. 2 solutions for m are those two things there. Okay, so I'll park those to the side for a second. Remember, I'm only looking for 4 tangents, and I already know one of them, so there should only be 3. So, when I take these 2m values and put them back in there, it feels like I'm about to get too many answers. But anyway, let's go to the second one with the plus and the minus here instead. So let's add these in, we get this. Let's square this, we get this. Similar ideas, this cancels with this, which is nice, so we end up with a nice linear solution of that. Now we've got 2 to go, so now we've got the minus plus 1 to do. But of course, when you do this, when you take away this from both sides, you get this. And when you square both sides, this just squares out to a positive, and you just end up with the same thing we had here. Because when I square both sides, if there was a negative here, it would just do the same thing. So I don't need to go any further with this. And likewise, when you do the negative negative and you add these in, you get this. But this is the same as, where am I going? Wrong way. This is the same as this one, right? With the negative there. When I squared it out, it became positive. So we don't need to deal with this either. So we have our 3m values. Those are the only ones we can find. And what we're going to do is we're going to put them into here to find some c values. Except this is quite nice, because when you put 3/4 or minus 3/4 into here, you're going to get the same thing, because m squared is just going to be the same thing. This makes 25 over 16, which is 5 over 4, which cancels with this 4. Oh no, yeah, sorry. 25 over 16, which roots to 5 over 4, cancel this 4 to make plus minus 5. And when you put in 7 over 24, you get this. And this is where this comes in, very handy. This is 24 over 24 squared. Then you put them together to get 7 squared plus 24 squared on the top, which is 25 squared, which roots to 25 over 24 squared rooted, which is 25 over 24. 4 divided by 24 is a sixth, I believe, so this will be 25 over 6 plus or minus. So okay, we have lots of potential lines here. We have these 3 different m's, and we have a couple of different c's that correspond to different m's. And what the mark scheme did here was it took the other equation for c that we built, the one back, where it's all the way back here somewhere, this one here, and it substituted in those m's into here as well to justify which c values were definitely right and which were wrong. I think that's too much effort. What you can just do is you can bust out your basic picture again, which I tried to draw more accurately here with the vertical line now. And you can say, okay, well, one of the lines has a negative gradient. The only negative gradient is minus 3/4, and that must be with a plus or a minus 5. But we can see it's going to be a plus 5. So that's good, we have that one. There should definitely be an x there. I've genuinely given year 7s detentions for not writing an x on their y equals mx plus c bits here. So, yeah. So, okay, this line here, now this line has a flatter gradient than this one. We can see they would sort of meet, because this circle is smaller than this one, they would meet over here somewhere. So this gradient's flatter. So that must be, of the 2 positive ones, they're not parallel, of course, this one must be the 7 over 24. And it's got a negative gradient, so that must match with minus 25 over 6. So I think that's that one. And this one has a slightly bigger gradient, so that must be 3/4. And that's got a positive y-intercept, so that must be plus 5. And I think I have this line, this line, this line, and this line as my 4 that are tangent to both. That's the whole paper. Thanks for watching.